right? So this is my first year as part of Peer, and I'm delighted to be here, and and to try and understand the talks and appreciate them. This started because my colleague Khalid Musalam said, we need an air force post disaster. And that has been sort of the motivation and vision that I've been working with. I am Raja Sengupta, and this is joint work with Professor Shikyang Chen, who's a professor at Kansas State, and he is a structural engineer. And Benjamin is there in the back. And Gaofang, I guess, is not here. He spends most of his time in the Richmond field station, except this morning. And Shin is the lead PhD student here. She could not be here. She is away presenting another paper at a conference desk. And Atri Banerjee is an excellent high school student who's now applying to college, and a very, very good guy. So this sort of, shows the motivation. We acquired, pictures of this church, and we want this aerial fleet. So we want multiple drones, right? And then, on the control console, this is what you see that, that you control the aircraft. There are multiple aircraft imaging, and there are 3 feeds coming in, and we want to be able to divide up the task and all that sort of thing, and then piece things together after that to construct a picture of what is the damage and what exactly has happened, right? So that is sort of the vision, and we're looking for efficiency in this. So the drone sensors that we consider, right? So we want to be able to manage multiple aircraft in some efficient way, and the sensors that we consider are LiDAR and cameras. Right? The LiDAR, because it gives you depth information, is very good for localization of the drone, and of course accurate 3D reconstruction. But I believe a lot of structural damage is seen on a camera and not so much on a LiDAR. Right? For example, finding cracks by actually differentiating depth information can be extremely difficult. Right. So there's also a camera in the picture. You see all these kinds of graphics from the consultants that everything is going to be 3 billion and 10 billion and 30 billion, and but a lot of this depends upon the intelligence. How much overhead this entails, right? Because the typical method is you send out a drone and it collects information, then you come back and you do what you can with the information. And if you don't have exactly what you want to send it out again, right? So this process needs to become more efficient for all this scaling to happen. And so that's what I'm calling the intelligence challenge. Can we put enough intelligence in it to make this process more efficient? And then there's, of course, the endurance problem. Because the quadcopter lacks the elegance and efficiency of a wing, and so these aircraft do not fly for more than 30 minutes, 40 minutes, right? And if you're trying to work on something like the Bay Bridge, I don't know if the quadcopter will ever get there, right? It may be necessary to use a fixed wing aircraft. But the intelligence and endurance problem are related in an interesting way. So, of course, flying 100 aircraft, right, is a logistical challenge, especially on a single PI, single graduate student peer budget, right? So what we've done in order to be able to explore things anyway is build a simulation environment, right, where we can do this, and then hopefully someday, we will get an agreement with Caltrans or something, and we'll actually be able to do this stuff at scale with real aircraft. So the challenge here, of course, is to be able to build a simulation environment that can simulate sensors properly, right? And that's difficult, right? And so we are using a gaming engine called Unreal Engine. And on top of Unreal Engine, there's something called SM, which is not our work. And then on top of that, right on top there, UAV inspection system, that is our work. That is the control intelligence. Right? And we connect it to the simulator through something called ROS. ROS stands for Robot Operating System, right? And ROS has become the de facto standard on all kinds of robots, whether using ground robots or drones or etc. So in that sense, there's a degree of realism because the control software that we're putting into the UAV inspection system would port directly to hardware because it's running on top of ROS. And SIM actually grabs, what exactly a LiDAR would see from a particular vantage point in the environment and gives it up to us. We acquire it through ROS and then process it into the control system. And there's a 6 degree of freedom model and all that, and that's the picture that's been shown on the other side. So while the drones are flying in simulation, right, we do actually, want to make sure that, in order to see if we can do 3D reconstruction, etc., we do actually fly. So this is right here at the Richmond Field Station. This test is Professor Mohammed Mustafa, right, who is cracking a concrete column, and we are trying to see if we can, do all this imaging and capture all this stuff in some efficient way, right, where and we can detect the cracking and spalling and all that sort of thing, right? And that's GovHorn, actually. So I'm going to skip this this video and show you, right? So this is basically the formulation of the problem. The single drone problem, that if you enable a UAV equipped with the LiDAR and camera to autonomously explore a volume and map any structure within it to a adequate level of precision and accuracy, right? And here you see, so that, we would specify this box and, we could give prior information that this is where we think things are, or we need not give prior information, right? And then we do this search. Now, the solution architecture looks like this. So let me focus on this box here. So there is the virtual drone. You may use GPS, you may not use GPS. The reason, if you're so this system actually does not require GPS, and this is why we use simultaneous localization and mapping, which allows the drone to localize itself, right, while it's mapping. So it knows where the structure is, and it knows where it is relative to the structure. The problem of relying on GPS is sometimes my understanding is that, when we're doing this kind of imaging, we want centimeter level precision. So if you want centimeter level precision based on GPS, then you must know everything, every rivet and bolt in your structure to centimeter level precision in latitude and longitude, right? So this can become very challenging. So this is why we have felt that reliance on GPS is not a good way to go. Hence, we use this technology of simultaneous localization and mapping, which keeps constructing what is known so far, tells us where the drone is relative to it, and then based on that, we plan what is called the next best view. What's the next best place to look for, given the inspection task that I'm trying to do? So most of our control intelligence sits here. And I want to say a little bit about this. I put it after the end, but let me just go there and explain what we do. Because so essentially what we do, we can think of this 3D volume as built out of cubes or triangles, right? And these cubes, they are either known and occupied, or known and free, or unknown, that is yet unexplored, or unreachable, like that black one, that this is an internal volume that the sensor cannot reach, right? So this is some solid object. Now, this is where, right? So there's sort of this question in our mind that when you take robotics and you take structural engineering, where can you bring them together, right? So this is where it's in this next best view where we can bring them together, because one can provide a distribution, right, based on structural understanding of where the damage is likely to be, right? And that is what can be used to speed up the efficiency of the search and mapping and discovery, etc. Right? And then as the drone collects information, does its real-time scan, one can update that damage distribution, the conditioned upon the observations that have been received so far, right? And then in order to select the next best view, we can define some cost function of that distribution. And robotics will say the most general way of doing it is to use the entropy. Use the entropy of the distribution, because essentially we're trying to make it precise, right? If I think of damage as an indicator variable 1 or 0, we want to know where it is 1 and where it is 0. We want to get rid of the uncertainty, right? So this is fundamentally the architecture, right, that we are using. So here you can see, this algorithm in operation. So the drone is flying in simulation, right? Because if I were to fly it really over there, I would have put in a bunch of obstacle avoidance intelligence, which is not really, there's no research component there, right? But of course, if we really fly something, we'll have to do that. So if you look at this aircraft, you'll sometimes find that it's going very far away, right? And then it's coming back, right? If we look at this thing, and let me explain in a minute why, right? So as this thing is flying, it's building this visualization, right? And every once in a while, it kind of goes far away, right? You can see with that red corner there that it goes far away. And the reason that it does that is that, so we looked at it and we thought this is an error, but actually what it is doing, it is trying to see the base of the column. And if it is very close, then it doesn't see the base because of the frequency of the LiDAR. So the intelligence is actually working correctly. It goes back so it gets a proper view of the base. And then sometimes this thing also rises on top. We have given it a ceiling, right? So that's why you will see that the, sorry, where was I? We've given it a ceiling. So it doesn't build the top part of it. Oops, trying to get this thing to play. Okay. Can you just play it, Amarnath?
Yeah. You want to go somewhere?
Yeah, in the middle. Let's go a little further. Yes, exactly, over there, right?
Okay, and it's playing.
Yes, and so at the end you'll see the 3D trajectory, right? Where it, you can see as it's traveling, the reconstruction is happening, and those corners are an express view. There's also an express view here, right? So where it goes there, and eventually you'll see. I think it's there, right? You see that it's actually traveling in 3 dimensions like that. And okay. So okay, and then of course, so the accuracy, right? So as it is flying, it's constructing a point cloud, right? So we look at 2 measures. One is the accuracy of damage location, and this is actually done post process, right? This is actually, so we are not yet doing this real time, right? So in order to, if we actually wanted to include the damage distribution, probability distribution inside, then we would have to do some of this computation real time, right? Which we are not yet doing. And here we are using pretty standard stuff, right? Like a yellow detector, etc. You know, we pick this up from the structural engineering literature, and we do this, and we get, I think the average error is okay, 3.3 millimeter, 4.1 millimeter, etc. Right? And then the other accuracy that we look at is the accuracy of the 3D reconstruction of this thing, right? So we look at 2 measures. We look at completeness in the sense that we define the spatial resolution, say 1 centimeter square. If we define the spatial resolution, then we want at least 1 point, right, which is close to that 1 centimeter. You know, we take all the biology, we project it down to that little cell, right, and say, yes, if there is a closest point there, right, then we have covered this cell. There's at least 1 point, and then we look at the distance, right? The perpendicular distance between that point and that part of the surface, right? And by that measure, the accuracy, average accuracy is 5.9 millimeter. Completeness, you know, it should completely explore all of the unknown volume, right? So there's some 2 point something % left, which I'm not exactly sure why, right? So we have to still figure this out. So that pretty much brings us to where we are. Looking ahead, there are a couple of challenges other than the big vision, of course. So currently, what is happening with these algorithms, right? They're running in simulation, and they would work on a quadcopter as you put it out. Because with a quadcopter, I have one big advantage. So even if, you know, so the drone flies to the next best view, it looks at it, it collects data. And then, even if it takes me 1 minute to process that data and update my model and decide where to go next, right, by processing my probability distribution and all of that, the drone can stay there and hover for 1 minute, right? Now, this is not good for endurance, right? I'm wasting time. Secondly, if I were to deal with the endurance problem by going to a fixed-wing aircraft, the aircraft would not come. It would keep going. So there is, so the intelligence problem and the endurance problem do have this connection, right? Other than the fact that a fixed wing aircraft is in general. So one direction of work needs to be to be able to speed up the computation, right? And so there we are looking at certain techniques in robotics to see if we can speed up the other thing that needs to happen is, of course, you have to move all this to fixed wing aircraft, right? Because I really think that if you're going to do something like the Bay Bridge with that kind of span, it will have to be a fixed wing aircraft to get the kind of precision that you want. And then, of course, this was a proposal that we submitted to PR last year. That so I've been looking for regional scale damage models, right, which are at the fidelity of use and test with a sensor. So that's the difficulty, right? And so when we submitted this proposal, we submitted it with a professor in Portugal, right, who actually reconstructs, renders. The right word is render, right? She actually renders 3D models at a city scale with damage simulations in them. And I need it rendered because then I can actually capture what a LiDAR sees, right? If you give me an OpenSea model, then I cannot capture any, it doesn't have the detail to tell you what a sensor is, right? So that's the kind of model that we're looking for, and then we could test things in simulation. And then, of course, I hope we get to work with captions and bridges. So I stop there. Thank you for your time.
We have time for a question.
Yeah.
If you had real-time analysis, then I presume your path would change substantially if you drove, because you can inform that path, right? And it would probably be much more efficient than just sort of a random walk.
Yes. So this is what we are doing here in simulation. So the algorithm, that's exactly what the next best view planner is doing. That as the drone is looking at things, it is absorbing that information,
And making decisions.
updating the model, and then saying, based on what is unknown, here is where I want to go. Right? We've not yet gone forward to say, okay, this is unknown and this is unknown.
Right.
But the structural engineer says that place is likely to need more information than that place. So the progress that we've made so far is actually we've set up the architecture, and now we have a box in which the structural engineering knowledge can go. That's been part of the issue, right? So if you want to bring two things together, to architect it in some clean way. Right? Yes.
More?
Yes.
More of a practical question.
Yes.
So it seems like the drone, based on its current path, decides on what to do next.
Yes.
But have you actually implemented it in practice? Have you actually tried it with the drone in practice? All the ones that I flew past,
Yes.
you upload the flight path, it goes wherever it needs to.
Yes.
You upload another flight path, go to the next one.
Yes.
How is that? How are you guys thinking that?
Yes. So if you just use the standard autopilot, then that's what you do. Right? But we don't do that. The drone will come with an interface of the drone. So under that interface lies the robot operating system. The robot operating system will actually allow you to send a point to the next test view. If you go there, and you can set it up so that the drone will hover while it's there until you tell it to do something. In the meantime, you can run queries on the sensor to pull back the data that you want. And then you process it, and then you can do it. So you can actually put this two ROS into the controller. Yeah. Yeah. You have to control it at the board level.
Okay, well, it's time to move on to the next speaker. Thank you very much.
Okay.